And this plot here is showing us an animation, polar projections. We're looking down the North Pole, right? So here's the west coast of the United States. We're looking at here at an animation of the speed of the westerly wind at 250 millibars. So this is in the upper troposphere. Okay, and this is just the westerly wind speed, right? And so this animation goes through the entire year. It's every pentad, which is every 5 days. It's a new word you can use. See you in a pentad. People are like, what? Try it out. So what we're looking at here is as we go through the seasons, here we're going into fall. We notice that the jet stream starts strengthening and intensifying. Strongest, again, off the east coast of both continents. As we move into winter here, the jet stream strengthens. It moves a bit further south. Okay, but you'll see where the jet stream is weakest. It's weakest basically just a bit further west of the U.S. and just a bit further east of the west coast of Europe and even North Africa. And this is mainly the subtropical jet stream. When you average things out, you tend to minimize things like the polar jet stream. So this is mainly the subtropical jet stream. And here we move into summer. Jet stream weakens. It moves poleward. Some of these are at 50 degrees, 55 degrees north latitude. What time of the year do you expect to see the most precipitation? If we know that mid-latitude weather systems require a jet stream to propagate along, this would actually tell you quite a bit about what time of the year you would expect most of the precipitation to fall, or at least the most frequent precipitation to fall at different locations, just by where the jet stream is. So here we move into February. Jet stream is pretty strong at southerly latitude, 30 degrees or so. We move further north. Think about a place like Alaska, right? When does it get most of its precipitation? The jet stream's too far south. It's not getting precipitation until we move into summer. As we move into summer, the jet stream starts moving further and further north. That's going to bring some systems that propagate along the jet stream into Alaska, in addition to convective precipitation. Convective precipitation can occur in the absence of a jet stream. All it needs is warm surface temperatures, enough moisture, and no subsidence that's going to cap it out. So that becomes important in explaining some of the precipitation seasonality. Okay. So we're going to pull these things together and think about how precipitation and circulation are coupled. So I mentioned already the sort of ingredients you need for precipitation. And we can talk about these things as they pertain to meteorological events. So this past week, the reason that we saw precipitation is we had strong southwesterly flow, a lot of moisture being directed from the subtropics, rising air meets topography, and you get a lot of moisture that gets squeezed out. I think I recorded something like 1.3 inches of precipitation in the last 2 days. That's pretty good for this time of the year. It's also been extremely warm, which tells you something about the air mass. There's a lot of ways to actually get uplift in the atmosphere: frontal systems, orographic effects, and then convection. Convection can occur either in a system itself, in a mid-latitude weather system, you can develop convection, but convection can also occur where we just have the right ingredients without any sort of large-scale disturbance in place. Okay, so the things that can determine your climatology of precipitation, first of all, is the jet stream. Okay, so where you get those temperature contrasts, that's going to set up where the jet stream is and where the mid-latitude eddies are going to propagate through. As mid-latitude eddies propagate through an area, they're going to drop precipitation on that area. And then we have things that are happening at the surface or the lower levels in the atmosphere. So surface heating can drive convection. Okay, air mass rises, we develop condensation, etc. You need more than just heating to produce precipitation, because we've all been in a desert and we know that it doesn't precipitate a lot there. You need to actually have some moisture that is being advected into that region. So we think about how the lower levels of the atmosphere, say the lower 5,000 feet or so, how the flow is occurring in those regions, whether we're bringing moisture into a region or taking moisture out of a region. Right? The main thing for precipitation is bringing moisture into a region at a rate that's faster than you take moisture out of a region. So if you have a net flux of moisture into a region, you're accumulating moisture in that region, and it must either stay in the atmosphere or precipitate out. Right? It's going to precipitate out much easier if we have some way to make the air mass rise. So that can happen through these dynamics. Also, topography we know plays a pretty big role. Right? That's going to force air mass to rise as well. So we'll start off by the global scale. And this animation here is just showing us a climatology of precipitation. Okay, 30-year climatology, more or less. So we'll watch this a few times. The data quality here is not great. This is from a reanalysis product. So it's not actual observed precipitation, it's model-derived precipitation. So the numbers obviously will vary quite a bit, and these are core scale estimates, but we'll look at the general patterns. Okay. So what's the first thing that catches your eye when you look at these? We have a very interesting depiction spatially across the globe. And obviously things like how much does it rain in a given location is an important attribute for a number of things, including the distribution of species, where people want to live, water resources, all sorts of resources that one would derive from the land itself. We see a couple things here with these precipitation patterns over land. Number one, highest amounts generally in the tropics where we have the ITCZ. These are areas that are receiving 100 or more inches of rain a year on average over pretty broad areas in the absence of having any significant topography that can greatly enhance precipitation amounts. You move immediately poleward of that, you are in a region that is affected by permanent subsidence, the descending branch of the Hadley cell. So very, very dry amounts here in the Saharan desert. Somewhat also you see here in the interior western United States, although this is a function of both that descending branch of the Hadley cell in the springtime, not so much in the wintertime, and topography. So we'll have to bring that back into the equation later. You look at Australia, which is actually very, very interesting. So it's wet in the north, it's wet in the south, and it's dry in the middle. Right, so what's going on in Australia? We have the northern part of Australia actually is in the ITCZ for part of the year. What time of the year would you expect the ITCZ to be most influential in northern Australia? Why December? Why winter?
Because the winter, the summer moved to the south, and the ITCZ moved to the southward to Australia.
Yeah.
During the December.
So peak thermal heating in Australia would be in DJF, December, January, February, and the ITCZ then would sag further south, and maybe the furthest south it's going to get is 20 degrees south latitude or so, right? In southern Australia, right, where actually probably most of the population is, there's an increase in precipitation. What's that due to? Is it the ITCZ? Yeah. That band of low sea level pressure that basically circumnavigates the latitudes between, say, 50 and 60 degrees south latitude. So that actually can eventually move far enough equatorward during a certain time of the year to bring precipitation to the region. That's actually just due to the jet stream. So if you look at the distribution of precipitation in southern Australia, during their winter, the jet stream moves further equatorward, northward, right, equatorward, and that allows for precipitation to happen more frequently during their winter versus their summer. The jet stream moves further poleward. It's weaker, less potential for systems, eddies, to drop precipitation in their area. So their climatology, in terms of the time of year that they receive precipitation, is somewhat analogous to what we see in Mediterranean Californian ecosystems, where you have dominant winter precipitation and then dry, warm summers. Same basic thing that happens here as well. It's mainly due to the jet stream moving north and south. In some areas, you actually get a combination of the jet stream plus convection coming into play. That actually happens quite a bit in the East Coast. So we'll take a look at a few climagraphs, sort of like what you guys all made, and we'll see how some of these differences arise. So the previous plot I showed you was annual average precipitation, and while some people might care about that, if you're a water manager or you are a critter, and you really care about a reliable amount of precipitation or water for your survival, you might also care about this, precipitation variability. Okay, and this is just precipitation variability. What it's really showing, I think, it doesn't actually say here, but this is the coefficient of variation of precipitation. So for those mathematically inclined, you can calculate the standard deviation of annual precipitation, right? And then you just divide that by the mean annual precipitation. So for Moscow, our annual mean precipitation is about 25 inches. And I don't know what the standard deviation is, but I'm going to make it up. Say it's 5 inches, right? So that would give us a value out of 0.25 or 0.2, right? That would give us just an idea of what that variability looks like. So here we're looking at just how variable precipitation is, annual precipitation is. What are some of the features that pop out? The deserts. The deserts are very variable, right? That's the main thing that I see as well. So we just looked at Australia. You see the interior having a very variable amount of precipitation. Also the Saharan region. Now if you look at this equation here, if you have a low mean, right, you don't change your variance, then this precipitation variability would actually increase. But the deserts are also an area that are renowned for species that are opportunists. So given extremely wet conditions, they're able to take advantage of those conditions. They're also able to cope with very dry conditions. That's a really key component here. If you look at the United States, what we also see is that the variability in precipitation sort of adheres to this notion of sort of the deserts having high amounts of variability, wetter regions having lower amounts of variability. But the one area that is quite renowned for water issues, even though much of the state is actually pretty wet, is California. So California's got the Sierra Nevada region that's actually can receive a lot of moisture, but it's also prone to high amounts of variability. Okay. Anybody have any ideas why that might be? Why might there be high amounts of variability in precipitation in California versus the Northwest?